So we're going to pick it up with choosing with versus without replacement. So this is definitely something we have to dive into and get into the weeds a little bit. So a couple questions back, we were drawing from a deck and we were always replacing the card and having it shuffled before we drew again. So that is called with replacement. You replace the card before you do the next component of the event or the outcome. But you could also do these things without replacement, and we see that a lot. When choosing multiple objects, it may be performed with replacement or without replacement. When choosing objects with replacement, we take the product of the probabilities as normal. So that's what we did a moment ago. We were always replacing the card, so we just looked at it one at a time. When choosing objects without replacement, take careful consideration to the number of ways the next event can occur and to the total number of outcomes. And I don't know if that does much for you, but okay, take careful consideration. All right, let's just jump into number 6 and see how this works. It says cards are drawn without replacement from a deck of 52. Find the probability of each one of the following round to 4 decimal places. Okay, sometimes we see 3 places, sometimes 4. Part A, let's draw 4 clubs. And you see that on the screen. Number 6, part A, we're going to label the event A as meaning we draw 4 clubs, 4 out of 4. Okay? And they're not replaced as we keep going. All right, let's think about this, and well, it's all on the screen there, but we'll talk through it. So the probability of this happening. So you see, these numbers represent the first draw, the second, the fourth. The first, the second, the third, and the fourth. But we're not putting the cards back. Okay, so we start with a fresh deck. 52 cards. How many of those 52 cards are clubs? And well, clubs represent an entire suit. And if you remember from the beginning how many cards are in each suit, there are 13. Okay. The ace through 10, and then jack, queen, king. So 13 clubs out of 52. Okay, we're going to draw one of those. Doesn't matter which one. We're going to take one of those 13. So 13 out of 52 chance of that happening. And we keep it. Then we go and we draw a second time. But now when we go to draw this second time, how many cards are there to draw from? Well, we already have one. So there's only 51 cards, right? So it's out of 51. And how many clubs are there to choose from? Well, again, we already took one. So there are only 12 left. So 12 out of 51. Okay, so we say we draw that second club. And now we've got 2 clubs in our hand, and we go to draw a third card. Well, now there's only 50 cards, and only 11 of them are clubs. So let's say we get that next club. Now we got 3 clubs. We go to draw one more time. Now there's only 49 total cards because we got 3 in our hand, and there's only 10 total clubs. So 10 out of 49, and we're going to multiply each of these numbers together. Now definitely grab your calculator here and just put all that in. So the probability of A is 0.0026, very low probability of drawing 4 clubs in a row like that. Not even 1%, right? 1% would have a 1 right here. 0.0026, very small chances. But it does happen. You draw cards enough, you're going to see it. But on any one draw, very, very low. Okay. That was good. So we took careful consideration to how many cards there were and how many clubs there were as we kept counting. All right. Part B. Let's say we draw an ace, a king, and a queen in that order. Okay, so now we're only drawing 3 cards. First one's going to be an ace, then a king, then a queen, in that order. So I'll say event A is ace, comma, king, comma, queen. Just to note. the order and what we're looking for. All right, so here we've got three numbers for the probability of A. Let's talk through them. Okay, so we go up to that deck and there's 52 cards and we want to get that ace or one of those aces. Well, there are 4 aces out of 52. Okay. Let's say we get that ace and we're holding it. Then we go back to the deck. Now there's only 51 cards, but how many of them are kings? Well, because we drew an ace on the first one, there's still 4 kings, so 4 out of 51. And let's say we get that king, and then we go back, and now there's only 50 total cards. How many of them are queens? Well, there's still all 4 queens, so 4 out of 50. And we can multiply those. Again, just grab your calculator here. 0.0005. Even 0.0005. Even less of a chance than getting the 4 clubs? Yeah, because there are so many more clubs than aces, kings, and queens, right? There's only 4 of each of these. So the chances are even smaller than that, a lot smaller, honestly. Okay. All right, I like to reflect on that stuff. Let's go to number 7. This is a classic way to do things without replacement. You might think of this as a bit archaic. An urn contains 3 red balls, 2 green balls, and 5 white balls. After a ball is drawn, it is placed to the side and the next is drawn. So just think, it reminds me of like medieval times. So they've got this very, very fancy urn with these fancy colored balls inside, and someone, for whatever reason, is going up and drawing a ball out or multiple balls out. And we're just looking at the color. By the way, probability, just the whole notion of probability started, I want to say it was the 1700s. And it really began with, I forget who the mathematician was, very famous one. And his whole idea was to get an edge in gambling. He wanted to get an edge in playing cards and, whatever kind of version of, I don't know if they had our modern dice and our modern cards, what it was, but that was literally it. And in those days, I guess a lot of people had these fancy urns, and they maybe drew balls out of them sometimes. I don't know if that meant like you draw a certain color, then it's death. I don't know. Okay, anyway. Let's find the probability of selecting first a red, then another red, and then a green. And we'll round to 3 decimal places. So you see event A, I have described as drawing a red, and then a green. Okay, but in each time, we're not replacing them, right? It says after a ball is drawn, it is placed to the side, and then we draw again. Well, let's think. A red, a green. So that's 3 draws. So we'll have 3 numbers, and we just got to think through them carefully. So the probability of A. So we walk up to that urn, and we want to draw a red. Well, how many red balls are there when we start? Well, there's 3, right? The urn has 3 red balls. And we're going to divide that by the total. How many total balls are there? Well, there's 10. There's 3 red, 2 green, and 5 white. So 10 total. So 3 out of 10 chance of getting a red ball on that first draw. Okay, then let's say we draw that red ball and we set it to the side, and we're going to draw again, and we want another red. Well, now there's only 2 reds out of a total of 9. Okay, we get that second red, we set it aside, and for our last ball, we want a green. Well, oh, I have a 5 there. That's wrong. My mistake. We don't want a green, or we don't want, it's not this number, excuse me. To get a green, there was only 2 green to begin with, right? And they're both still there. My mistake. There are 2 green balls out of a total of 8. I might have to recalculate my answer. Let's see how it works. 3 out of 10 times 2 out of 9 times 2 out of 8. Oh yeah, this answer has changed. My mistake. 0.017. Okay. There you go. So not very good chances, less than 2%. Which you would expect, right? Exactly red, red, green. I mean, okay. Very nice. And now we need to go on to and events. Let's chat about that. What if two events, A and B, both occur and A influences the likelihood of B? All right, so two events both occur, but the fact that A has occurred actually changes the likelihood of B to occur. All right. Obviously, we'll get to examples in a second. We've got a new notation. You see what's written there. Let me kind of get us set up for number 8. You see that notation. This it means you would read that as the probability of A, excuse me, I'm just mixing all kinds of stuff up right now. The probability of B given A. So that line right there, you read as the word given. The probability of B given A. So we're thinking A has already occurred. So what are the chances that now B occurs, given that A has already occurred? And of course, it's important that if A has already occurred, that changes the likelihood of B. Maybe it makes it more likely, maybe less, we don't know. But it changes it. Okay. So then we see this formula just below. I know it's on the screen there in that document, but I'll just go ahead and write it. The probability of A and B is equal to the probability of A times the probability of B given A. So we have these two events, so it makes sense that we're going to multiply them. In the past, we really thought of this like the probability of the one simply times the probability of the other, right? And we just think of them kind of as occurring separately. But the fact that this has already happened now changes this, changes the likelihood of B occurring. So we got to think of that second one as, okay, A has already occurred. So what are the chances of now that B occurs? Because that's already happened. And then that's the chances of them both happening. There's definitely a connection here with, the like drawing cards without replacement, right? So if we wanted to draw, an ace and then another ace, or a club and then another club, the fact that one club has already been drawn changes the likelihood of the next club on the second draw, right? Okay, let's get to practice number 8. We're going to do we're going to kind of sit in this for a little while and do a couple of practice problems. And practice number 8 really just gets us set up for kind of used to situations where, the likelihood of B changes given that A has occurred, and this new formula we got there. Okay, let's go ahead and I'll read practice 8. An insurance company found that 53% of the residents in a city had homeowners insurance with the company. Okay, so 53% of the people in the city, they've got their home insurance with us. That's pretty good. They got a pretty strong hold on this market. Of these clients, 27% also had automotive insurance with the same company. And so there's a key phrase there that tells us it's this given situation. The key phrase is of these clients. So they're not talking about everybody in the city anymore. They're just talking about the people who have homeowners insurance with them. Of these people, 27% have automotive insurance with the company. Okay. And then at the end, if a city resident is selected at random, what is the probability that the resident has both homeowners and auto insurance with the company? All right, let's dive into it. And I'm going to describe here at the top the two events. Okay, so there's two things going on, right? So people have homeowners insurance with them, and then people have automotive. So let's think of A as a randomly selected city resident has their home insurance with this company. The resident has their home insurance. And event B is that any randomly selected resident in the city has their automotive insurance. Okay. So then what have they described to us in those first couple of sentences? Well, this one is a little bit easier to wrap your head around. You know, they told us out of everybody in the city, 53% have our home insurance. So the probability of A is 0.53. Out of all the residents in the city, 53% of them are with us for their home insurance. What did they tell us in that second sentence? Of these clients, 27% also had automotive with the company. They just told us the probability of B given A is 0.27. Why? Because they're only looking at the people who have their homeowners insurance. So assuming this person already has our home insurance, what are the chances that they also have auto insurance with us? So what's the chances they have auto insurance given that they already have home insurance with us? Okay, and it's 27%. So then the question, what is the probability that the resident has both homeowners and auto insurance with the company? So there's the and. What's the probability of A and B? So if you just pick any random person in the city, what are the chances they've got both their home and auto with us? And well, from our formula, we can see I need the probability of A times the probability of B given A, and that's going to give us our answer right there. 0.1431. And you kind of look at that and you think, well, so many people in the city have their home insurance, but not a lot of people have their auto insurance, right? Of the people with their home insurance, I mean, 27%, and maybe they specialize in home insurance, and auto insurance is kind of this other thing they started just to maybe get more business, but they're really not known for that. And so it turns out in all of the city, only a little more than 14% have both home and auto with them. Okay. Keep scrolling in the document, and we'll talk about this idea a little bit more. So it says it is often desirable to calculate the probability of B given A. Usually, it's not the B given A that we're told. Usually, this is the number we're trying to figure out. And so in this case, and we've got a new formula there. Technically, it's not a new formula. It's actually this same formula here rewritten. So the formula you see, what they did is they isolated the probability of B given A. Essentially, they divided both sides by the probability of A, and then those would cancel, right? So it's obviously, the left and right are switched, but the probability of B given A equals probability of A and B divided by probability of A. So typically, we know these two and they allow us to find this. It's okay, but it's the same formula, just rewritten a little bit differently. Okay, let's check out number 9. All right. The probability that Sam parks in a no parking zone and gets a ticket is 0.06. And the probability that Sam cannot find a legal parking space and has to park in a no parking zone is 0.20. Okay, so Sam, um, he's he or she, Sam often parks in no parking zones, and I don't recommend that. So, but that seems to be the case here. So, and what are they telling us so far? The probability that Sam parks in a no parking zone and gets a ticket is 0.06. Okay, so that's one thing. Now, if you park in a no parking zone, are you guaranteed to get a ticket? Well, no. Maybe nobody comes by, or maybe you're not there for that long, or whatever. So the probability that not only does Sam park in a no parking zone, but then in addition to that gets a ticket is 0.06. And that's probably higher than what we'd like for ourselves, but at least it's kind of low. And the probability that Sam cannot find a legal parking space and has to park in a no parking zone, has to is kind of like, did you really have to? Okay. Is 0.20. So it's pretty common for Sam that when he or she shows up, and it's going to be at their school, their campus, when they show up to their campus, there's just nowhere to park, and they decide, well, what am I going to do? I have to park in a no parking zone. Chances of that, 0.20. Okay. So on Tuesday, Sam arrives at school and has to park, there's no alternative, has to park in a no parking zone. Okay, so this has already occurred. What is the probability that he will get a ticket? Okay. Let's dive into this. So, event A is that Sam has to park in a no parking zone. And event B is that Sam gets a ticket. So what did they tell us in the description? So when we read that first sentence, that's the and, right? The probability that Sam has to park in a no parking zone and gets a ticket. So the probability that both of those occur is 0.06, A and B. And then the second part of that sentence, the probability that Sam cannot find a legal parking space and has to park, so we can trim it down. The probability that Sam has to park in a no parking zone is 0.20. So that's the probability of A. I have to park in a no parking zone right now. On Tuesday, Sam arrives at school and has to park in a no parking zone. Okay. As it begins the question, we see that Sam has already parked in a no parking zone. That's already occurred. So what are the chances that he will get a ticket? So we're saying, what is the probability of B given that A already happened? We know he's already in a no parking zone. What are the chances that the ticket now occurs? And we can use our same formula rewritten. It's the probability of them both occurring, A and B, divided by the probability of just A occurring, 0.20. And here we'll get the answer. I'm going to expand on some of the thinking here. Here, the probability of getting a ticket given that you're in a no parking zone is 0.3 or 30%. And we've got the answer. But let's go a little bit further, and just why this formula is what it is, and maybe maybe I can explain a way that's helpful for you to remember this or make some sense of it. So I have that Venn diagram there in the lecture document. Another perspective on the probability of A and B comes from the Venn diagram. So the Venn diagrams were developed at the same time as probability in the 1700s. And here we've got, kind of your standard Venn diagram. So the big box we call the sample space. So that's everything that might occur. And then within that, we've got these two events. So there's the A and the B. So think of A for us as the chances that Sam parks in a no parking zone, and B as the chances that he gets a ticket. Now, one thing I didn't mention in the problem, is it possible that Sam gets a ticket for some other reason? Maybe Sam parks in a legal space, but still ends up getting a ticket. Yeah, that's possible, right? There's other reasons to get tickets besides being in a no parking zone, right? Like you roll a stop sign, or I don't know. Or, whatever, your parking pass is expired, or you never bought one. Okay, right. So there's other reasons to get a ticket. So we've got event A there, and we've got event B, and there's some overlap. So sometimes, it's possible for them each to happen without the other, and it's possible for them both to happen, and that's the shaded region in the middle. Okay, so how does this help with our problem of the B given A? So if you think about that formula, let me write it again. Probability of B given A. The probability of A and B divided by the probability of A. Okay. Looking at the Venn diagram, we're thinking, okay, assume A has already occurred. If A has already occurred, then we know we are inside of that A circle, right? That purple circle. We're not in anywhere in that sample space. We know that we're already inside of A. All right. So now what are the chances that B will also occur? Well, if we're already inside of A, then the chances for B to occur would just be that middle shaded region. Right? So I know I'm inside of A. If B is also going to occur, that would mean it's the overlap of A and B. And so what we do to find this probability, we really just go back to that first formula for calculating probabilities, right? The number of ways something can occur divided by the total. It's just here, the number of ways, if you will, for B to occur is limited to that overlap. And for us, we know that that was the 0.06, A and B, right? That's the shaded region. And then when we divide by the total number of ways, then we're dividing by the total number of ways that A can occur, because we know we're already inside of A. So it's like the shaded area divided by all of the area in A. The number of ways B can occur divided by the total ways we could be in A. Probability of A and B divided by the probability of A will tell us that right there. In fact, even this symbol, which seems kind of strange and foreign, right? That vertical line, that comes from division. That's like the root, right? Probability of B given A, it's like we're dividing by A, dividing by the probability of A. And that's a good way, even to remember. Sometimes people get confused on, well, how do I maybe I remember A and B goes on top, but I forget that it's probability of A down here. How do I not mix that up? Because there's the division symbol again. It's like you're dividing by A, divided by probability A. Okay. Hopefully the Venn diagram makes some sense to you, and I've got a description there at the bottom, really rephrasing what I just said out loud. Let's stop this video here.